Hello and welcome again to Big Ideas at Microscale. My name is Hemdeep. I'm joined by my co-host Robin, and today we've got an amazing guest lined up. I think the one thing that I've always enjoyed, at least for over the last 5 years, is been able to talk to those that are not PIs or running the main research, but really speaking to whether master students or PhD candidates, because they're sort of that go between the actual project, the technical part of the project, the actual procedure. Like they sort of bring together everything together in one cohesive piece, and then they end up pushing that project through. And so today we've got Chen from McGill University. Hi there, Chen.
Hi, happy to be here.
So why don't you give us some quick background to exactly what you do at McGill, the team you're working with, and things of that sort.
Yeah, sure. So I'm a third-year PhD student now with my PI, Christopher Morais. And we do a tissue engineering, but we are still considering cells a bit as a black box, but we look at everything that goes around the cells. And that's why the name of our lab is Cellular Microenvironment Design Lab. What we do in general, in general, it's basically what I do, at least. It's I fabricate some sort of device, and I put cells in and see how they react to the thing we want to subject them under. And so we're a bunch of engineers trying to do a lot of bio stuff at the end of the day. Yeah.
So what kind of cells does the lab work with? Does different lab members have kind of different specialties, different cells that they're looking at?
Yeah, we work with all kind of cells out there. Like I personally already work with epithelial cells, but I also work with organoids, which is basically which has all type of cells. Other people, a lot of cancer cells, also other kind of organoids. Yeah, it's not limited to. We're not limited by the type of cells, really.
Mm-hmm. And what kind of got you into tissue engineering in the first place?
Oof, that's I think it could be long, could be short, but so my background as undergrad is chemical engineering, and but I always had an interest for the bio side, because to me, bio was something that it's first still at the beginning, of science, kind of like compared to like some of the like physics, right, or chemistry, where it feels like a bit done, but I know it's not. But like at least I felt like bio is very much at the beginning. So I was interested in bio, and as a chemical engineer, there's a couple labs, at McGill that does tissue engineering, like bio related stuff. So that's how. A bit also. Chris was my teacher for one of my class, and two of my class. I really like his teaching and his style. I think that has a big part in it too. That's why I chose his lab and the tissue engineering. Yeah.
I think I noticed, I think over the weekend, I was talking to my son who's just starting to apply to universities. And I think there's a huge difference between the time that I went through the university system and what's available now. And I think that the options that are available during undergraduates for undergraduate program is so amazing in terms of the type of programs that you can take. You can try so much in terms of subject matter. Can you give us an idea of what kind of subject matter you had taken in your undergraduate that sort of helped you drive towards this project that you're on right now?
Yeah, so it's true. I do think chemical engineering is it's a very old program, but I do think McGill does very well at integrating a lot of like the newer courses like biotechnology and things like that. I think like the traditional chemical engineer, but as like a process engineer, wouldn't have had. And we have like bioprocess engineering, and we cover like a very broad spectrum, I would say. It's and also some of the more advanced class out there is also offered as a elective to undergrad. So if you're interested, you could really choose that, right? Like plasma engineering, like polymer science, all that thing, right? So really, it's I think McGill is doing a good job at offering like more modern chemical engineering course than just the traditional process engineering.
So then what courses did you meet your professor, Chris Moraz, at?
So he taught the fluid mechanics, which is was a tough class, but I think I managed to get an A after going to his office, like because there was an error, but we had to argue a bit, and I managed to get an A in the end. That was good. He also taught a class called Instrumentation and Measurement, which I actually TA'd for many years after I took the class. And in that class, you really try to build some device, try to use all your knowledge that you acquired throughout your chem eng degree and build a device to try to answer a real life question, right? Which is very like how that class was framed. That's the two classes that he taught.
Mm-hmm. It's very bold of you to argue with your professor.
Oh, you gotta do what you gotta do to get that A in the end.
Of course. I bet he probably appreciated it, considering that you're in his lab now, right?
Yeah. And he told me like I was like the only student he remembered to have argued for a grade. I was like, really?
Oh well, yeah. I think there are many kids who argue for the grades. I think they seem to always rise to the top, and they usually are all standouts whenever they start doing any post-grad work and everything like that.
Oh, okay. I'll take that.
Yeah. No, it really is it's a really good personality trait to have. It sort of, you stand out, and you also carve out your own path, and you get noticed very, very quickly. Yes, you get noticed for being a bit of a pain in the ass, but it's still valuable. It's still, it means that you're willing to push convention, and you definitely stand out as a result.
Speaking of pain in the ass, I remember I was like doing a little bit digging, into your profile. Sorry about that. And I was on the Moraz lab, and I looked at like the people section, and there's this very interesting paragraph, and it's like, occasionally you break equipment soon after you use it.
But there's no hard proof. There's no hard proof.
There's no hard proof. Yes, that's. I think this is what it actually said. Occasionally, equipment breaks down suspiciously soon after it is used by Chen, but there's no hard evidence that proves he is responsible.
Yeah. That's actually interesting about that was like that was actually my my grad supervisor. So I started in this lab as an undergrad, as like a summer undergrad student, and back then my grad supervisor, like I showed him my paragraph, and he was like, "Wait, let me make some adjustments." So he actually wrote that part. Because I do think back then, like I'm a bit bold in how I use the instrument. I'm not that careful. I just kind of use it. I don't really care. And maybe it's me. I don't know. But it did happen pretty often back then when I was an undergrad. Yeah.
Can I ask what instrument you were using?
I don't know. It's been so many years. But there's a lot of sometimes like new instrument, right, that we have, and we have to kind of try to figure it out. Like I remember we got a plastic injection molding machine back then. So I was not like careful with it to not break it. I was just fully testing it, like trying to get the thing done.
So I guess product manufacturers should all be reaching out to you and just giving it to these brand new equipment so that you can fully test the capabilities and the absolute limits.
Beta
test everything.
Yeah, if that role exists, I hope that.
I think let's first talk about epithelial cells. You mentioned it just earlier. That's the type of cells that you specifically work with. How about you tell us a little bit about that, what they are, kind of like its purpose in the body, I guess.
Yeah, sure. Yeah, so epithelial cells are basically cells that covers the inner outer lining of your body. So like your skin, your lungs, your stomach, they're all covered by epithelial cells. Is the most common cells in your body. I wouldn't be able to tell you like in like a bio-wise like exactly like other things. That's a bit of like a common theme in our lab. Like when it's past a certain point about the bio, we don't know anymore. We're gonna ask a biologist to explain it. But for our purpose, it's like enough of understanding, right? We kind of just know how they behave, how we differentiate them, things like that. Yeah.
Epithelial cells are in the category of adhesion cells. So in terms of if within the range of all sorts of adhesion cells, do you guys sort of work with a whole range of adhesion cells, and how do you exploit the actual key thing that you're looking for as well?
So we don't really like categorize the cells by like those are adhesion cells. We have other projects that look at the adhesion property
Okay.
of those cells, and like for example, one of my colleagues is injecting some kind of sensor to expand and see how much it expand inside of a cell aggregate, and that would kind of give an indication of the cell adhesion in the cell aggregate. But it's not. We don't see it as like a related related thing with like between epithelial cells also being a adhesion cell. Yeah.
So what is the specific functionality of the epithelial cell that you're trying to sort of examine with the projects that you guys have right now?
Okay, so the property I'm trying to examine is how they differentiate. So I can go a bit more about my projects. So
Yeah.
basically, when you culture epithelial cells, especially like the let's say the lung epithelial cells under air liquid interface, which is culturing the cells so that like one side has access to liquid and the other side gets exposed to air, they start differentiating right into this realistic phenotype, like into like the same cells that you have in your lungs. And that's how we make those in vitro model, right? To then do drug testing, do kind of testing on those cells. And yeah, so my work is really to kind of explore that, like all the intricate property that factors that goes into it, and what actually makes this air liquid interface work. Because right now, when you think about it, it is like a weird way that we are culturing cells to make individual models, like a culturing this, but because we don't really know why that works fundamentally, right? There's a lot of things that goes in it, and I'm like exploring a small part of it, which is the hydrostatic pressure, like the pressure that's getting pushed under the membrane, like which is inherent when you create an air liquid interface. And I'm looking at how that affects the differentiation in that process.
And I think when you're for the air liquid interface, there's a specific setup that you're using, I think with transwell inserts and everything like that, right?
Yeah, so originally when the idea was first proposed, right? It always goes like that, where like my PI will have an idea and just, how can we build a device to test that, right? So I was like, okay, how do we put the pressure on those epithelial cells? Originally, because we do a lot of microfluidics, we thought of doing something microfluidic wise, have a PDMS device and somehow add that pressure on the cells somehow. But then I just thought, how about we build a prototype first that takes the existing commercial transwell and just try to build a device around that to induce the pressure. And that took a while to kind of get together and work, and we kind of just stuck with that and never got back to the microfluidic version of it, which before I think we'll try to just stick with that to fully figure out the biology behind it before we try to optimize some kind of a microfluidic device for it.
Mm-hmm. There's like a very interesting, I guess, image or schematic where it shows kind of like how the device works. When we first did our Zoom interview, that's where you kind of like presented that to me, and that really helped me kind of get a better idea of how it works. So we'll be sharing that with the audience.
Nice.
and so they can see it as well. But because you had a media reservoir, so how did the entire setup actually come together? Like, how did you build that up?
Oh, it's just putting things together that we already have in the lab, pretty much, right? So we have if I want a media reservoir and kind of raise it, then the easier way is to connect a media reservoir through a tubing to the compartment in which you want to induce the pressure. So it's really much just gathering things around in the lab and then find a way to put it together without affecting cell culture. So you have to think a bit in advance there, like you can put the super glue anywhere directly because then that would affect the cells. So you have to find out a way to piece it together. And yeah, that's a pretty rough prototype. We actually move away from that schematic, like that prototype. I made some like more like a easier to make version where I just plant a vertical tube inside the bottom compartment. So then I can just with help of some 3D printed parts, and then that allow me to use less media too and easier to make. Yeah.
And I think so. It was actually the hydro. Talking about that model, right? You tested as well how the cells differentiated, or if they did, with like a gel-soaked media, and it didn't work, right? From what I remember.
Yeah,
So
that was actually not from me directly, but from another colleague, in our
yeah.
kind of colleague in our lab who also did a lot of work on this on this lungs differentiation work, and it wasn't really like her main project, but she tried to culture those cells on a gel, and then still have it exposed to air, which is technically still air liquid interface, but she just couldn't make it work. She couldn't get it to differentiate anyway, and that's what gave my PI the idea that maybe is that tiny pressure difference that when you put in a transwall, that kind of did something for the differentiation.
No, I was just about to ask you, what kind of difference in pressure are you looking at that causes these type of differentiations?
Yeah, so in the normal transwall, it's really only a couple millimeters of pressure, and it's not regulated at all, right? So it's very technician specific. Some people might add a bunch of media in the bottom compartment. Some people add just enough so they barely touch the cells, but usually it's just only a couple millimeters of pressure. Versus in my device, I really increase that to kind of maximize that effect.
And when you applied the pressure, the hydrostatic pressure, was the only differentiator marker the thickening of the epithelium, or were there kind of other indicators that the differentiation was working?
Yeah, so we first started with lungs, and lungs was it was the thickening of the epithelial, which we call the pseudostratification of the epithelial, was very obvious. It like had a direct correlation with the amount of pressure I was applying. So we were super happy about that. But one thing that we didn't get is, as well as the air interface, which is another marker, is the formation of those ciliated cells. So some cilia on top of the epithelial cells, which you do have in your lungs, right? Like a bit of those cilia. And those we didn't get it as much as the air liquid interface. That's what made us think that. Okay, so instead of thinking, this pressure thing as the way of the only thing that matters in that differentiation, it might be just one contributing factor, and by controlling pressure, we might be able to have a better control of that air liquid interface differentiation than if we didn't know about this variable. And then later we switched. We thought, if it works on lung, maybe also what works on the intestine. So we had a collaborator from Belgium who came here for around a year, and she was like the expert at gut organoid, and so she helped me culture gut organoid into a monolayer on the transwall, and we also apply pressure on it, and that we can clearly see like a morphological difference under pressure. Like the cells looks totally different than the control, and also aortic interface. So we've been trying to figure out what's happening to those gut cells for a while, and that unfortunately I think is not going that well. Like it's something's happening, but it's not really the air liquid interface differentiation. We're still trying to determine like what's happening with those gut membrane. Basically, we see those vacuoles forming inside the membrane, and we're still not sure what that is. We have the RNA-seq results, so we're still doing the analysis to try to identify what that vacuole is. But I do think we might just at this point we might switch back to continue working on the lungs, since it was working so well on the lungs. Yeah.
So when you did start developing this one for the gut, did you just take the protocols that you had set up for the lungs and just move it across, or was there any changes that you had to do to the protocol to adjust for the environment for these cells?
Yeah, like organoid cells, organoids, they're very difficult to culture, and that I so before it was that collaborator that was culturing them for me, so I kind of took it a bit for granted. So like I thought it would be kind of similar, right? But it's a lot of small things that you have to take into account. Like for organoid, you have to maybe coat the membrane a bit differently. You have to add this and that's different. All that small things, and but yeah, until I started doing it myself, because then she left after a year, so I took the protocol and started, and that's when I realized like how much more difficult it is to culture those gut organoid compared to just epithelial cells. Yeah, I was definitely taking it too much for granted, the work that she did for us. Yeah.
So I think I read that the air and liquid interface technique is it considered more of a 2D model just because the cell growth is like on a flat surface, right?
Yeah, exactly. That's we basically break that 3D organoids into single cells, and then we seed it on the membrane to make it a monolayer. So yeah.
So then you were testing as well the effects of pressure in like a 3D model, or was that like what you're currently working on?
Yeah, exactly. That's something I'm currently working on. We're trying to see like what kind of pressure the organoids is under in a 3D model, because we know that they're kind of embedded in a matrigel, which is like a hydrogel that they need to get nutrient to grow. And as they're growing, they're also pushing right against that matrigel. So there's some type of pressure there, and also we know there's like a luminal pressure that's forming at the same time. So we're trying to really have a closer look into what type of pressure those 3D organoids is going under when they're growing.
And what's kind of the importance of like this difference between like 2D models and 3D models? Is there something like 2D models is missing where it's necessary now to start looking at 3D?
This is a very generic question in the field. So 3D models has been getting popularity in the recent years. There's a bunch of reasons why this is more accurate in terms of model than 2D. But one of the easiest answer would be just like, we are 3D creature, right? There's a lot of cell interaction, cells property that's not recapitulated well in the 2D models. Okay,
so it's just to get as close as possible to like a human, like the actual physiology of a human body. Okay, that makes sense.
Yeah, that's something that, yes. Yeah.
So I guess a 2D model is really just only focusing on that membrane interface, but there are obviously missing parts as you scale up to a 3D model that you need to worry about.
Yeah. So that's not to say that 2D models are not as useful, right? Like 2D model is still very useful in terms of like sometimes we have to isolate variable because 3D model is so complex. There's so much thing going on in there. Sometimes you still need to go back, break it down into a 2D model to really see fundamentally like control the variable and see what's changing at that level. So it's not to say that 3D model is like better than 2D. Exactly. Yeah.
So what were kind of like the difference and challenges when it came to testing 3D modeling? I guess it's just the complexity, or was there like anything more specific that your lab really struggled with there?
it's I came to the like I learned that culturing those 3D organoids is really much an art. It's like it took me a while, like even following like the protocol. It's there's a lot of intricate stuff that is also very technician specific, and sometimes you just have to be able to tell that here it's this thing's not going well because of this, and none of this you can't really find a lot of stuff in the literature, right? Because it's so new and not a lot of people has published a lot of things about it. It's not general knowledge, so it's pretty much of a like I would consider like an art right now. Like something you just like, yeah, I see this, what's happening. Oh, maybe you should add a little bit of that the growth factor, right? Which I can tell you why we have to do that, but there's a lot of things that makes it a lot harder than just normal epithelial cells or primary cells that it's you can pretty much just have to follow the protocol and it just works every time, right? Organoid, very often you just some batch just doesn't work, or some patient derived organoid just this patient just doesn't work, right? There's I think there's one patient that works very well for us, and we're all super glad for that patient to write the organoids. Just it works way better than the other ones. Those kind of small things that makes it a lot harder to culture.
Were you able to identify what was it about this specific patient that is working well, or is that like it just is what it is?
Yeah, that's that for me at least. That's I'm okay with that answer. Like this patient's cell just seems to grow a monolayer like better than the other patients. Like, I really don't know. Yeah.
Okay, so what kind of luminal pressure did you actually identify in the 3D organoid, and how did you measure that pressure?
Right. So originally we had this ambitious idea based on one of the paper to somehow incorporate those microbubble sensors that change depending on the surrounding pressure. And we came to realize that those it's actually a very hard that would be very hard to do on those micro bubble sensor, and also like just to be able to characterize the tiny change inside the lumen.
Mm-hmm.
So we've been trying to look at more, just get kind of have a simpler approach, which is just adding our existing microgel sensor. So we in our lab we have this super soft hydrogel that we can make it very small, integrated with cells, cell culture, and they'll deform under any kind of forces, right? And then we can kind of measure the forces around in that in that area. So so been trying to just stick with that that sensor and just trying to get it inside the organoid, get it around the organoid, see the pressure against the mesogel, and see get it inside to look at the change, the forces that those organoids are experiencing on the inside. And the thing about luminal pressure is, I think it's liquid, right? It's a liquid pressure, but those lumen don't even happen most of the time. Very often the organoid is still just dense. So there's a lot of things that we need to kind of work on and solve before getting that luminal pressure.
Can you describe luminal pressure in terms of how would it be traditionally measured, and what is it that you like? How did you initially propose to test it in these organoids before you decided that it might not be a strategy that was well worth doing?
So traditionally, I think one of the method would be to have this it's like a very small kind of like a needle sensor that you have to poke through the organoid to get a pressure reading. We were not thinking of doing that. It's a bit outside of my expertise, but we thought that those microbubbles, which under ultrasonic wave, they would vibrate a bit differently depending on the pressure around those microbubbles, right? That's when we thought it might be feasible to do it like this. But then to be able to see that change, I think it will require some characterization method that we were not ready to we didn't think that we would have.
But the other, because you use a different type of sensor as well, like the very soft one. I believe it was called EMSGs, but I'm not really sure exactly what that stands for. Is that something you're still using, even though you got rid of the microbubbles?
Yeah, no, that's the sensor basically that I pivot to, because it is a pretty famous sensor around our lab. So it was done by a previous, like a senior PhD student who graduated already, and that sensor actually got very popular, and a lot of people in our lab is using it just to get an idea of, so when you want to have an idea of some kind of forces like in your culture. It's very easy to make, and you can just add some in your culture, and they'll kind of be everywhere. And when you get lucky, then you'll find one exactly at the spot that you want it to be, and you can get the force measurement at that spot.
Okay.
And how does that one work? Is it some sort of foreign substance that you put in there, or a gas, or another material that allows you to measure it?
Yeah, it's basically a hydrogel, but that it was tuned to be super soft.
Oh, really? Okay.
Yeah, it's tuned to. Yeah, I don't remember the exact like the whole whole softness measure about it, but yeah, that's I kind of just use it now. It's I don't remember the exact. I think it's
Okay.
And how do you kind of incorporate the sensors into or onto the organoids? Because I know it's surrounded by a matrigel, right? So, like, what is the process of actually getting that sensor on there?
Yeah. So originally, I thought of to get it the sensor inside the organoids. I would have to try to make the organoids with the sensors.
So, like,
that's
grow
why,
the organoid around the sensor.
yeah, somehow just really pack it together.
Okay.
And but then that's I think I showed a schematic of like one of my undergrad project where I was thinking just like having a funnel where I can centrifuge all the cells together with whatever you want to add. But then as well, I didn't need to do that. Like it really didn't want to get in allo at first, but I figured that as I split those organoids, so basically splitting, it's I break the organoids apart and then regrow them into each organoid. As I split those organoid with the sensors, very often they end up being inside of the organoids, and that's because I also coat the sensor with something that's my organoids like, right? So that's something that people have to take into account depending on the cell culture that they're using.
So now, so there is, I think, a fairly famous paper discussing the controlling pressure differentials in 3D organoids, written by Nikolov. How did that paper inspire the project and the device that you're creating right now?
Yeah, so that paper is really, I think, when we saw we were able to get access to the lumen side of an organoid and the outside of the organoid. Like before, that organoid would just be a clump of cells and which have a lumen and it's just enclosed and it's not accessible, which is like when you think about like a real organ, right? It's real organ are always accessible to the lumen. That's how they have to function. So with that kind of model in which you can have access to both sides, then I think that would allow us to do a lot of studies that would be more accurate and relevant to the real world. And so when I first started working that for another PhD student that already graduated, his idea was to make placenta models within those devices. But unfortunately, we never got it fully to work well before he graduated, because it's actually very hard to laser shape a pattern inside a hydrogel. It took us a while to kind of get something to close, but not enough for that PhD to use it for placenta model. But then we thought like, oh, like we could use it for my project, right? Where because now we have access to both sides, then it will be very easy to regulate, try to find a way to induce a pressure that induce a pressure that would have an effect on one side or the other. Because before that, if you just put an organoid under pressure, it will kind of just equalize on both sides. We wouldn't have like a gradient of pressure across the membrane, and that's what we really need for my project.
So so for the placenta project, that was just your regular clump of cells. Is that right? And then now you have your unique shape that you kind of developed.
For the placenta project, it was we didn't get anywhere except for putting some cells inside whatever the shape that we carved. The placenta. So we didn't really grow anything like an organoid.
Okay.
Yeah. But right now that the plan is like to see if you could replicate that paper, which is actually a lot harder than we thought to do than we thought it was, which is always like that when you try to replicate a paper. And then see if you can find a way to induce that pressure somehow, like very easy with a liquid column, right? For example, on one side or the other.
So that device then that you're trying to replicate, are you fabricating in the exact same way, or do you have your own methodology for that?
Yeah, no, actually that's where the 3D printing comes in handy, right? Like before, to get anything to fabricate something of that resolution, especially there's some micro pillars involved that holds the hydrogel, the collagen together. For those kind of features, you really need the SU8 to create the mold to get anything for that at that resolution. And that's why actually we decided to buy the Microfluidics 3D printer. It's because it was said that we can make a very high resolution PDMS device, and that's the approach that we pivoted to make those devices from now on. Which I'm super glad, because those SU8 mold that we had, only 2 of them worked out of 6. So I could the productivity was very low, right? Like every time I could only get 2 devices to work out the 6 mode that I have. And if there's something you want to iterate, there's really not you can't do it that easily on the SU8. There's a 3D printing, just crank out another mode and just if you want to have a feature that you want to test, it's very easy to iterate.
For your specific device, like what was the time difference between the SU8 mold versus like the 3D printed mold?
SU8 mold. I was fortunate enough to not having to make those SU8 mold. It was from the PhD student that graduated. But I know that he spent a long time, right? Like with a lot of alignment process, that he had to build his own device to align the mask. It's a huge pain.
And did you find that when you started using 3D printing that you can now deploy different strategies of orientating certain model features or exploring other features in the Z or anything like that on your side?
Actually, like for example, some device, not for like a PDMS device, because PDMS that's still I think we have like just like a height limit before it becomes too hard to peel off and make.
Yeah.
But some like existing like just like a one piece device, then yeah, definitely, right? We can a lot of things that before you have to add, let's say for my liquid column, you have to kind of piece something else like a tube or something to it. Now you can just print it directly in that direction. But in terms of a microfluidic device, I think like we're still limited by that the mold that we're making, right? Like if it gets too tall, then the mold doesn't, the PDMS piece doesn't come out as well.
So for the columns, you said you also 3D printed that?
No, that's actually for another device, one of the side project that our PIs are making us do, and we use a lot of 3D printing for that device. It's basically we're trying to integrate a membrane on which we can culture the device. So maybe I could use it for my project. I don't know. Maybe we're trying to integrate a membrane inside a microfluidic device that's directly printed using a 3D printer. And for that, to induce the flow, we're thinking to just use a liquid column, and it's super useful that we can just print it directly, right? Instead of having to add another liquid column.
Is there a reason why you chose to 3D print it? It's just like out of convenience, or
yeah, I don't think there's other ways like to make that device at this point. Instead of also it's convenient, as in our hope is to eventually just put a 3D printed device in all the biology lab, so that every time we make something new, we can just send them the file and the protocol, and they could just get
print
the device. To print it up themselves, right? So we try to make it as easy as possible to make, like no third party the component and things like that. Just like ideally it would be one piece. They just click print and they can get the device that we developed for them to use.
It's interesting because we've talked to a couple of like other researchers, and they all have that kind of same vision where you can share kind of devices amongst each other, because now it's a digital file, right? And as long as you have a 3D printer that is able to print that out, it's very now easy to kind of share that knowledge and build that community around it.
Have you noticed that, is there any sort of limitations that you still find with 3D printing that you wish could be, areas of improvement? I know that there's always a need for new materials. That I think has become one of the biggest things people are always asking about. But what is it that you would like to see improvements in 3D printing?
That's the biggest one, is definitely the need for new material. Like for our field would be have those resin that's biocompatible. That would be very useful. And there's a lot of I think progress on that recently. Like we've seen paper getting out about those clear biocompatible resin that the lab make themselves, that still seems to achieve like a high enough resolution to be useful. That's for sure like the biggest one. And other 3D printing, now that I'm thinking about it, I could see improvement. It's maybe for like resin specifically, that's what something that we're trying to figure out, right? As we're making this like membrane embedded device, is like there's no easy way to stop and go that much. To stop and go. Like I think ideally we would. Like an FDM 3D printer is so easy to just stop and add our thing and keep going, but I think it's still very hard to do on resin. I don't know how that would be solved, but I think that's something that's missing compared to like the flexibility of the FDM 3D printers.
Yeah, that's true.
So as you kind of progress through this, your line of research, is there a bigger picture? Are you looking to, once you have these in vitro models done, is there like a sort of disease that you're looking to kind of diagnose using like the differentiator markers or anything like that?
Yeah, so that's where like I'm a engineering background, right? Yeah. I really enjoy making those device and for whatever needs is out there, but. I personally wouldn't have like a bigger goal of looking at a specific disease that's like way outside my my expertise.
Okay.
I enjoy like making the device. Like when my PI tells me like, oh, can I make a device to make this, like to test this? I was like, oh, cool. I'll try to make that happen. But when it gets too bio, like that's the thing where like I don't even have like the confidence to be able to look into things like that. But bigger picture on my side would be. Trying to fully characterize the effect of the hydrostatic pressure, and then see if you can popularize that to some kind of like a new transwall product or something else that we develop that so that is the norm, right, for anyone who's trying to do those air liquid interface differentiation. So that they first know about the effect of the hydrostatic pressure, and second, they can also have an easy product to use to help them induce that hydrostatic pressure.
Now, I also understand that you've co-founded a new lab called LabGiant. Why don't you tell us a bit about that venture of yours?
Okay. So it's not a lab; it's online. It's an online platform, and I can go more into it.
For sure.
So basically, when I started my master's, I noticed a lot of things that was not as efficient, as I would like it to be. And you know what they say, right? Like when for engineer, when something doesn't work exactly how they want, they're trying to find a way to fix it. That's basically essentially what I did. I saw, once I think I had to characterize a sample and I just didn't know how. And then eventually we managed to do something. But then after a while, I saw like an equipment that exactly I thought I could use in another lab, like that they weren't even using. It's just collecting dust. Just like, okay, that makes no sense. Like we should know about things like this to make it more efficient for everyone. That's when I realized that a lot of labs in academia works in silo, right? Like we don't really know the other labs' equipment expertise. A lot of professors end up buying duplicated equipment. That's a lot of money wasted too. So that's why we made this marketplace that's designed for research labs, where they can share all kind of resource, equipment, whatever expertise, even digital files. They can just put it on there and it'd be super easy for other users to find, to look at what's around them. And even for some of the more niche tools, right, that let's say the hydrostatic device I made, another lab might be willing to try it out, but they don't know how to make it. So I also put that on the marketplace, right? Like they could just get it from us. I'll ship it to them for a small price, and I think that'll be much more efficient way of collaborating than our current way, which is usually it's like you have to read a publication. You like that publication, and then you try, like I did. I try to recreate that publication, and very often it doesn't work, right? Because it just lacks the detail, right, in the methodology to fully replicate it. So I think like a more efficient way would just be directly collaborate through the work, right, through the product, right. If one lab is really good at making it, then just sell it to other labs, and then we can just grab the work and keep going. I thought that was very similar to if you guys are familiar how why software engineering has been able to progress so quick is because they have this system on GitHub where they can just grab the code and just keep going with the code. They don't even necessarily understand what was going on with that code. That's why software engineering has been able to progress so quick, right? It's this like very efficient system at building on each other's work. And that's what we're trying to build with LabGiant.
I'm actually on the site right now while we're chatting, and how do you find time for this? I'm looking at this. I'm just going, this is a well laid out site. It is extremely intuitive. I can see why any lab would want to be on a platform like this.
Thank you. It's really, I'm very glad to hear this.
Oh yeah, because and you're right. In terms of collaboration, it is extremely valuable, especially in the research field. There is a lot of duplication that happens, and I've always found that if you can figure out a way of getting someone someplace faster, you'll always find a marketplace for it. And this certainly, I'm just taking a quick look, and I'm quite wow. And do you guys have access to the next gen AI? That sounds like something that that we need to explore further. Are you going to be creating a large language model for microfluidics?
That's the goal. So basically, as we were having all those database of equipment resource, what we realized is that even me, right, I'm a third year PhD student, and a lot of those equipment, I have zero idea what they do, especially when they have a very technical name. Like no one knows what a thermal ICP 3000, like I don't know what that does, right? But AI would know. AI would know exactly what that does. So we implement AI so that they can recommend you the equipment resource, just depending on your needs. So basically, you really have to tell our AI bot what's your problem, what you're trying to solve, and our AI will be able to guide you. Just you might want to use this equipment or use that resource or look at this expertise from that lab, and guide you around to help you find those things easier for you. So I think that's we showed it to a lot of professors. They also thought like it was like a game changer and how we would do research, because as the large language model gets better, I think you'll give like everyone out there like a baseline of how to do research, right? Of like how to think of a solution to a problem. That's our goal for LabGiant.
Yeah, this is Fantastic. I can get lost in this rabbit hole of tools and technologies here.
Yeah, no, that's why we have an export page, right? The homepage where you can just like, if lab have something new publication, something new tool that they build that they want to share, you can just scroll the export page and just, oh, well, maybe I like this. I want to try this, and just click the link and get one from them. I think that's our vision for LabGiant.
Great.
And are you looking to get labs all over the world on board of this, or is it like regional?
I know you're right. Like we're starting with McGill, still refining a platform. There's a beachhead to the market, but no, I think it absolutely makes sense to build this network of research lab around the world, so that we can all collaborate, right? Like see what's out there too.
Amazing.
Yeah, no. About the first question, like, how do I find time for this? Like, the real answer, it sounds a bit bad, is just like not really caring about work-life balance at this point. just like now, it's daytime PhD, weekend. I work on this with my co-founders, who are software engineers, and they know that without them I wouldn't be able to make this happen, of course. And it's just a lot of sacrifice on time, right? That's all.
To be young again, eh?
Yeah, I think that's the advantage. Like I have to do this in my 20s, because if not, I don't think I have time to do this in my 40s.
No. All right. So if you do all of this work, how, I know you sacrifice life and work. Like, what do you do for fun? And how long in a typical week would you spend, split your time between lab work? Obviously you've got to do, you have to present and start developing your PhD work and everything. And then you have LabGiant. Do you breathe? Do you eat at all? Do you sleep? Are those optionals for you?
I try.
Yeah.
No, for fun, I think, I've been on the McGill varsity badminton team for a while now. And this was actually
badminton? Oh, wow.
Yes, I do play badminton. Yeah. Wow. But this was actually my last year to be on the team. So it's, I think it was time to me to retire, and then, from badminton, and I'm looking into like some other activity I could do, not just to stay in shape, but I would say that's the main fun I'm having outside of all the work. Yeah.
All right, then that's great. Again, thank you very much for doing this, taking some time out to chat with us. And
super happy to do this. Yeah.
And I think when this LabGiant starts picking up a large language model, we should have you come back on, because I think large AI is going to be extremely important for.
We're thinking of training it, like not only on database, but also everyone's like expertise, publication, and things like that. So I think that would really help everyone to just have an easy way to find the things around them for research.
Perfect. This has been a very informative conversation, Chen. This, I think we got a very good sense of exactly what you do at the lab, and then you've introduced us to this offshoot of your work life, where you sacrifice everything for the rest of us at labgiant.ca. And we will put the links to this LabGiant, so we'll add those to the show notes as well.
Thank you.
Thank you for joining us, first of all. It's been a real pleasure talking to you and kind of getting to know your work and what it is you do, all the devices that you've created. And I don't know if you've broken your own devices or if that's just other labs ones.
All right. Well, we'll see you around. Take care of yourself.
Thank you.
All right.
Have a good
Bye.
day.
Bye.